Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
Hi, I'm Dave Whitehead, CEO at Schweitzer Engineering Laboratories, and your host for Schweitzer Drive. In 1982, SEL's founder, president, and chief technology officer, Dr. Ed Schweitzer, invented the first microprocessor-based protective relay. His invention transformed electric power system protection by building a number of totally new capabilities into the device, including communications. Today, we're going to talk about all of the things this capability has made and continues to make possible with two experts from SEL, Ken Fodero and Paul Robertson. Ken Fodero has been at SEL for almost as long as me, which is a pretty darn long time. But before joining SEL in 1999, he'd been working in the telecommunication industry for more than 20 years for companies including Pulsar Technologies in Coral Springs, Florida, RFL Electronics in Boonton. Did I get that right? Boonton, New Jersey. And in his current role, Ken is a senior engineering development manager for SEL's wide area communication. Now, Ken, if you worked 20 years before you joined SEL, you must have started working when you were about, 3 or 4 or something like that? You're too young to have worked 40 plus years almost.
The funny thing is I left a few off from before the RFL days, and we'll talk about that a little bit.
I got to believe at some point somebody was violating child labor laws, but that's probably another podcast.
I appreciate that.
Paul Robertson is our senior product manager for our wide area network communication product line. He joined SEL in 2010 and brought more than 25 years of experience developing, marketing products for the telecommunication industry, including cellular, wireless, and wireline communication systems. He worked in a variety of technical and marketing roles for Motorola, Hewlett-Packard, and Agilent Technologies. And Paul, I think some of those companies were the same companies, just kind of swapped names. Isn't that about right?
Certainly did for Agilent Technologies. They came out of Hewlett-Packard. Yeah.
And you have 25 plus years before joining us. Again, it's like child labor laws were broken somewhere. I am pretty sure. Both Ken and Paul have authored and presented numerous technical papers on power system protection and communication topics. I think I've already said hi to both Ken and Paul, but hey, thanks for joining us. I'm really looking forward to this. This is going to be a fun and exciting topic. You know, the power system operated for many, many years without the need for communication. Certainly Edison and Insull didn't have, high-speed gigabit Ethernet connections between substations to ensure that the proper operation of power systems. But my goodness, has the ability to communicate, improved or created new ways to protect power systems, but also given visibility into our substations or electric networks all over the place. No longer do we require manned substations, right? And it's one of those reasons certainly is because of the advent of communications. Of course, with every new technology comes a host of new challenges and new problems that we have to mitigate. And maybe we set the stage too. When we talk about our communications, they're part of a control systems, and it's very, very different paradigm than it is, say, on the OT side or your house where you're trying to stream networks through some kind of network system, whether it's Verizon or Spectrum at my house, where I think it's more what we refer to, I guess, as a best effort technology, right? If my Netflix gets to my house, yay, I'm very, very happy. If it doesn't, I guess I go read a book. We certainly don't have that luxury of a message not getting through when we're trying to protect a power system. So to kick this off, will you talk about the history of communications and the electric power system? Ken?
Sure, and thank you, Dave. I think I reached back and I remembered a story a coworker at RFL told me once, and he said that his grandfather was the first current differential relay, and it was in 1940 in Hungary. He sat in a substation, looked at a meter, and had a phone, and another guy at the other end of the line looked at a meter and had a phone, and if the current moved very quickly, they called each other to compare notes to make sure that everything was okay on the system. Not exactly high speed, but that's the first story I ever heard of communications and protection.
Well, and to remind our folks how a current differential really works, right? It is the current going in one end of a line better equal the current going out the other end of the line, or it's spilling somewhere in the middle. And if that's the case, then we need to open up both circuit breakers at both ends.
Exactly. So when I first started, I worked for Westinghouse Electric in 1980. And that's even before RFL. And I did a lot of systems engineering. And in the systems at the time, they're using a lot of audio tone equipment that they were brand labeling. And I just fell in love with the communications part of the relay systems. So when I left Westinghouse, I went to the manufacturer of the audio tone equipment, which was RFL Electronics.
How'd the audio tone equipment work for our folks listening?
Very, very simple concept. I think if you broke it down to a baud rate, it was roughly, you could say it was one baud because you're sending just a single contact closure. But really what happened is the protective relays sensed a fault. They closed a contact, which keyed up the audio tone, which was normally sending out a fixed frequency. And then it would shift to either a higher or lower frequency. And that once it received that at the other end, it would close the contact, which would go back into the relay scheme and determine whether there's a trip. Seems kind of antiquated. And the whole process took about, high speed back then was in I'd say 9 milliseconds back to back, and low speed was in the 12 to 16
That's
milliseconds.
Still pretty fast, right? And it's, if everything's fine, you're sending a tone out, pick your 1200 hertz or something like that. And if there's a problem, you switch to 1600 hertz or something like that. That's a pretty cool system. So you have the channel is always, if something's running on the channel or not, because you should be always getting some kind of tone, if you will, out of the channel.
And back then, the primary carrier was leased telephone circuits. Back then, we only had AT&T, I believe it was, and they had standards for special lease lines for the utilities that offered the kind of performance that they needed. And that went on well for a long time. But interesting as communications technology changes, all of a sudden what works today doesn't quite work on the newer technologies. And it's been I think that's one of the most exciting parts of being around so long is learning how not to trust the next new shiny thing and what you have to do to adapt for it. Examples are when we went from analog microwave systems to digital microwave systems, the characteristics of the noise totally changed. And we all of a sudden went from this really secure high-speed audio communications to this, all of a sudden we're seeing misoperations and false trips, which means a false trip is the receiver is tricked by noise into thinking that it should send out a trip output instead of remaining in the guard state.
And that's not good, right?
Yeah, it could be very bad.
In our industry, you do everything right and nobody notices, right? And you have a bad day, as you mentioned, a misoperation, and you're on the 5 o'clock news. So
yeah, and that's always been a key driver. You don't want to make the news.
No,
and it was back then. I remember you listen and you hear something like a blackout on the weekend in the news, and you're always afraid to go to work on Monday to hear that, oh yeah, it was your equipment that was in the middle of all this. So back then we didn't have cell phones with fancy stuff. It was teletype. So teletype and analog phone calls.
So we start out with audio tone communication, and I bet there were a couple of others before that. But I'll use air quotes, the modern era, right? We went to audio tone. You're sending essentially 2 bits of information. One is don't do anything, right? But the channel's still up, or 2, do something, send that 1 bit of information kind of stuff. How is information being communicated, back when you were, a young man to today with the kind of information that we're sending in the systems that we're using to send this new information?
I think that's been, again, another exciting part about being around so long is evolving with the technology. The digital age was certainly super exciting and another opportunity to learn new things. So when we're talking, like if it was power line carrier or audio tone, it was the old analog signal to noise ratios. And then when we moved to digital communications, all of a sudden I had to care about bit error rates and Hamming distances and message design for security and reliability. The whole equation flipped, right? With analog stuff, it was how do I make it secure? With digital communications is how do I make it dependable? Because it's inherently secure if you design your messages.
What was the driver from going away from analog systems and sending 1 or 2 bits you just mentioned to new systems with bit error rates and Hamming distance and CRCs and all that other stuff? What is it that exploded that required us to move away from 1 bit to essentially many bits and bytes?
Again, that was another fun part of our history, right? And all of the major utilities had analog microwaves. And then came the PCS craze when all of a sudden everyone wanted to do paging and cell phones. And the FCC needed to reallocate a whole bunch of frequencies and basically kicked all the utilities off the analog microwave bands. But they got stood up on a new digital radio or microwaves and went to things like T1 carriers, where now instead of doing frequency division multiplexing, I'm doing time division multiplexing. And I can send a lot more data, a lot more high speed. And it's always better to go natively into communications media. So if I have a digital now communications media, it's a lot cleaner to put digital information into it.
Okay, that gets me thinking. So you're talking about the channel and how it's evolved. I think I'm thinking from the power engineer or the utility engineer, thinking what is he now filling up all of this bandwidth you just made available? Right there, it used to go from I just need to send 1 bit, trip or don't trip. Maybe it's 2 bits depending on how you think about it. To all of a sudden now I'm using 1 gig, 10 gig, 100 gig, data paths now. Maybe not 100 gig, but certainly we're using a lot. We're sending a lot more data. What is it that we're actually sending, and why are we sending all this information?
And I think you kind of hit on it a little bit earlier. We went from sending 1 to 2 bits for trip or don't trip. And now with the availability of digital communications, the wide availability of it, it enabled us to really double down and introduce schemes like line current differential, where we're actually digitizing and sending samples of the 8 local AC currents down to the other side of the line at high speeds. So it really enabled us to send a lot more information, a lot more precise information, and develop better tripping schemes. When I started out in this industry, like 12 milliseconds was screaming fast. And now with digital communications and the current technologies we're using, 2 milliseconds or less is where we're at. So
it's certainly amazing. When Ed came out with the first microprocessor-based relay in 1982, it certainly had the contact outputs that could key up something, right, to send the trip or don't trip signal to the other end. It also added a communication port on it, right? And now we have the ability to directly interrogate a device that's connected to the PTs and CTs. It's also making a trip decision. So you can get metering commands, you can get status information out of that stuff, and all of that has some value to an operator that's trying to run a large system. But of course, you need a communication channel to bring all that information back to some central location. So how did the advent of adding some, at least at the time, some high-speed communication at 9600 baud really change how we go about moving data around, or actually being able to move data around for the first time?
With the advent of the digital microprocessor relay, we could get event reports, fault information. The engineers don't have to drive 120 miles and go look at which flags dropped on a electromechanical relay scheme to figure out sort of what happened and hope nothing got jammed or stuck. And now at their fingertips, almost instantaneously, once an event happens, they could get online and, not online in the sense of we do today with, you don't Google a relay, but you could communicate with the relay and get all of the information about that event.
So if a little data is good, a lot of data is better, right? Is where we're trending to now.
Yeah, and I think we went through a phase where people went crazy and they wanted to download everything. And what people kind of lost track of is it's good to have a lot of data, but we really need solutions and answers, not be overwhelmed with data. So picking out the right data that is kind of an art form. So we went through one of those phases like, oh, I could get everything. And now people are, I think the devices got a lot smarter and provide just solutions instead of just all raw data. And it's a lot better.
Yeah. We're processing as much as you can locally is usually the best answer. And then just passing up results that an operator can take a look at quickly to figure out what's going on the power system. The way communications are used in the power grid are very different than, say, in the business or the office networks that we're typically used to most days that we're working. How do protection applications needs and performance differ from other industries? Paul, you take that one.
Yeah, thanks, Dave. It was very interesting, actually, just hearing you sort of reminisce almost on the history and the sort of trajectory maybe the industry took. You're moving away from analog-based communication and towards really digital communication. I think most people would say that their familiarity with communication technology tends to come from what we do at work. Maybe it's the PC, maybe it's what you do at home with your, downloading, maybe watching Netflix. And those networks broadly, we would refer to as best effort, which means that, you're going to get Netflix that may throttle the data rate that's coming into the house, depending on, who else in the neighborhood is watching. And that variation in performance, when you try and draw the analogy of the power system, that would create inherently a problem within the systems that are trying to protect and monitor the power system if you're going to try and throttle that data rate. And so there is this performance attribute that I would say differentiates what we would call an operational technology or a real-time system that's managing the power network. It demands very, very low latencies, and it requires a very predictable communication channel. So you must guarantee this performance that the applications then can rely on, in contrast to what I was using there as the Netflix kind of example, where it does vary. And, to the user,
we don't get the luxury of the little buffering symbol that if I don't have quite the strongest connection in protecting power systems is what you're telling me?
Exactly. That luxury just doesn't exist. And how you go about then designing the network then becomes very important. How do you then guarantee that performance for these types of critical applications becomes the challenge.
That's really interesting. And I think about maybe moving to the next thought here is one of the challenges I see with our industry is that we build a control system. It's working fine. And I think there's some thought that, well, let's let it run, right? It's not broken. So why go and fix it? However, we come up with new capabilities, new features, new ways to do things. So we like to modernize our power systems. And there's been a lot of that's been going on in the years. And so we find ourselves in a unique paradigm of having both legacy systems and new systems, and we'd like to integrate both of them if we can. I think in the IT industries, there's an upgrade of the entire systems, the IT systems, probably every 5 to 7 years or so. Like maybe it's even faster these days. Our systems here in the power systems or control systems industry, they just don't have that luxury, right? One is that we've got a lot of systems out there. They're spread out all over the place, and taking an outage or shutting down a substation, right, is, especially in the summertime, is just not acceptable. So you all, as communication folks, have a unique challenge of marrying the old and the new. How do you go about doing that?
From the early days, we went to communications. Our biggest concern was getting that one bit across a communications circuit. And today, multifunction relay, it has to securely, fast, and reliably get that signal across, but it also has to provide streaming data for synchrophasers. You have to have engineering access and enough bandwidth to download event reports. And there's also a bunch of analog telemetry, metering. The modern protective relay, it has a lot to say, and not everything is as critical. So, there are different priorities, of course, but when you look at it, that one device went from a 1-bit requirement to quite a bit of bandwidth per relay, depending on how each utility is using it and how much data they're trying to pull out of it, which is pretty fascinating.
Yeah, I think it's another interesting observation. It's really the internet. If people think about what's driving communication technology, a lot of it is internet driven. So the needs of the sort of bulk user is about getting access to, I go back to Netflix, but it's these types of services, these streaming services. And so you've got this interesting challenge where you've got this broad technology trend towards giving higher and higher data rates. As I mentioned before, this best effort, delivery of data, yet we are in a situation where we're dealing with designing for a completely different set of requirements and having to interoperate with those types of technologies, but preserve the low latency attributes and the deterministic pieces that we need for the power system, and also dealing with what would be, we use the term legacy, but let's just say older methods that may be audio tone based. And that whole mix is still in play today. And we're trying to look forward as well as dealing with the sort of existing infrastructure that may not be, utilizing those types of methods. And I think that is a really unique set of challenges that maybe many don't appreciate.
Yeah, we're still replacing old pilot wire relay devices. There's still a lot of audio tones on lease lines that people are needing to replace. So pretty much everything is still, a lot of these different technologies are still in service. One thing I'd like to bring up is the utility industry is not on the leading edge of communications technology. I used to think it was about 5 years behind the telecom industry. So it's really the big telecom providers who are driving it. And if you think about it, today, people don't have phones on their walls. There's no more, there's very few analog circuits that are still supported that aren't eventually converted to packet. People have cell phones. Most everybody has cell phones, and that's completely IP and packet based. And people spend more time browsing and using the data on their phone than they actually use for talking. So voice over IP has replaced the analog line. So we're in an industry now, another quantum shift, if you will, where the telecoms networks are now moving from that pure digital TDM to packet-based technologies. And it's, again, another one of those shifts where we have to learn how to successfully migrate the digital technologies today to operate correctly over the packet-based transports of today. It's been a little bit of a challenge.
Hey, what is that challenge? Let's pull on that thread for just a second, because I think you guys have done a remarkable job of, let's call it the brownfield or existing systems. The protection is working absolutely fine. The challenge, the way I see it, is the communication links are the ones that really evolved. And you talked about the big telecoms that are really driving that from the corporate level. And I think one of the attitudes is, well, if it's good enough for IT, it ought to be good enough for OT, right? And just hook up the wires or plug in the cables, and what could possibly go wrong. And I think you guys as communication experts, control system experts, have really found that sweet spot of how do you take legacy systems, understanding what the communication latency deterministic requirements are, and then morphing that into what I'm going to call these modern IT systems, right? So it doesn't have to be, you have to go with the big carrier or something like that, or you have to stick with the legacy systems. Rather, you built this newer technology that can accommodate the legacy stuff and the new stuff and integrate with the traditional IT systems. Maybe you can expand a little bit on that thread. I know just enough to be dangerous, I think, but I get really excited about some of the stuff you guys are doing.
Yeah, thank you. I'm trying to think of how to talk about that without getting too emotional. So well, first, take a step back. We have hundreds of thousands of relays in service, and our customers expect at least 20 years life out of those devices when they put them in. And those devices are based on technology, which we call now, quote unquote, legacy, which means it had a TDM-based interface for communications. And trying to transport TDM over.
And real quick for folks, right? TDM means about, let's just pick some random time, but it is every millisecond I expect to see, or 10 has to tell me something every millisecond. If I don't get it every millisecond, or you pick your
it's 125 microseconds.
It's 125 microseconds. I get a message from Ken. I need for my protection to operate correctly. I really need it to show up every 125 milliseconds, not every 121, not every 130, but every 125.
And the point you're getting at is it's not just that it gets there very quick, but it gets there very deterministic, right? So you can always count on it's going to take this long from point A to point B, and we can guarantee that. What we didn't talk about, time division multiplex, like you said, it sends packets continually. That makes it very, very simple to be that predictable. With IP or packet-based transmissions, as Paul was alluding to earlier, it could be best effort. There's a lot of newer technologies where we can take some of the mystery out of sending packets, but it's still a asynchronous network where you have a lot of packets entering a network and they all can't jump on the line at the exact same time. So there's varying stages of buffering for the data. I won't get too technical on you there, but what it results in is a variance in the delivery time for those messages.
And it makes sense, right? If my email shows up in 130 microseconds or 120, I really don't care that much, right? So it's the IT or the packet-based folks are solving a different problem than we were solving in the TDM world. And
the problem can still also be solved in packet-based networks. They're not evil; they're just different.
Yep.
And we need to understand how to make systems that work better with them. But back to my emotional part. I spent my whole career getting those 10 milliseconds out, and overnight we added them plus some back in the, trying to do this convergence. So some of the products and technologies we work on is how do we get back to those high speed interfaces? Because as you know, the speed at which you can operate a control system is important. If a fault is on the line, the longer it's on the line, the more equipment damage that can happen. You can run into stability problems on your power system. So the quicker we can make that fault go away, the better. Now, as you said earlier, the relays aren't designed to solely rely on communications, but when communications is available, we're going to save as much of the power system as we can.
Yep. It's communicate more, but rely on it less if you want to. But man, if it's there, you can really speed up protection. But you know what? Electric utilities aren't the only ones that, are running into this challenge of reliable communication. The ability to merge new with legacy systems is also important for them. What are some examples of, say, other industries outside the electric sector that could benefit from this merging of, say, the legacy and the new stuff?
Yeah, that's been a very interesting journey for us, I would say, over the last couple of years. Is we've been working with different industries on this challenge of essentially legacy methodologies, and one industry in particular that I'll draw on is public safety. So public safety relies very, very heavily on voice-based communication, and traditionally would use analog-based phone telephony. So back to what Ken was talking about earlier, this analog phone line, what others refer to as a plain old telephone system, was the backbone for essentially every communication device that was out there, and it based on a a analog phone line that gave you a nice circuit-based connection. So when you made that call, you had a point-to-point circuit path that you used for that communication purpose. Very reliable, and it did exactly what it needed to. It allowed two parties to communicate. Well, a large part of our public safety infrastructure relies on an analog-based telephone circuit to allow the dispatcher to provide to the first responder details of the incident. And they tend to run parallel methods, so they don't rely on just the analog line. They will also use typically then a digital method of exchange to provide that same information. But it's this redundant, guaranteed circuit path that they still haven't found an equivalent level of reliability to. And we were a little bit surprised as we entered and started talking, about solutions SEL had that could address this issue. Now, they wanted to maintain that integrity. So it's back to what we talked about earlier, this need for dependable communications, guaranteed when I need that service, I can make the 911 call. I know with 99.999% reliability, I will always be able to dispatch, whether it's the police or fire service. And so the challenge then is, okay, so if I have infrastructure that is using this analog-based methodology and the industry is driving towards modern digital networks, how do I maintain that level of service over a modern system? And not only that, I've invested in end equipment, analog radio equipment, etc. That is a cost. It's a fact of life that, just having a public entity try and migrate, if you like, all of that infrastructure onto, let's just say, a digital equivalent, a lot of practical challenges. So we've been able to solve this convergence, this ability to maintain legacy over a modern digital system with some of the products that we have at SEL, and do it with that reliability, that guaranteed deterministic delivery of data. And that's interesting, I think, from a broader sense. Even though we led the conversation today about the power industry, there are others like the public safety industry that have the same challenge.
So public safety systems and power systems, there's probably other industries that have a same or unique challenge of this brownfield and greenfield or legacy systems integrating with newer systems. And one of the big challenges has to be related to the education of workforce skills. I look at today as protection engineers. Not only do they need to be a great protection engineer, but they also have to be a PLC programmer, and more to what you guys are doing. They have to be network designers. They have to understand protocols. And these days, you have to be a cybersecurity expert, all just to get a bit from point A to point B. How is the industry managing all this?
It's been a real struggle. We have a lot of people who are retiring, so we've been losing a lot of experience in our industry. We have a lot of younger people who are coming up, and they're brilliant. They're a lot smarter and faster than me. They're version 2.0, I guess. And all they lack is the experience. And there's a little bit of a lost art in why do we try to do things so fast and so securely and dependably. So the education is a constant part. I think Paul and I probably spend as much of our time teaching customers and as much as helping them solve problems. It's a constant.
Is there a way to speed this up? Because this problem's not going away, and eventually you and Paul are going to retire, and then what do we do as an industry?
We do a lot of independent classes. We work a lot with other organizations who are involved in training, like the IEEE and other trade organizations.
Okay. Hey, this is for both Ken and Paul. This is your great Karnak moment, if you will. Looking ahead 20 years, just 10 years from now, what exciting communication innovations and capabilities are you most excited about?
We're capable of getting a lot more information than we used to be. I remember in the 90s, people had a T1, which is 24 of those voice circuits, and thought that's more bandwidth than they'll ever need. And then today, you look at the networks, and 10, 40, 100 gigs is where we're baseline. Is like, what are we doing? Where is all that information coming from? So I think we have the advantage of we could get a lot more data and a lot more information between locations, and there's probably unlimited things that we could do. I know right now all the rage is MPLS technology, and I know that a technology called segment routing is coming up next, and segment routing just helps things look more like the TDM system. So I think we're coming around to now the industry is getting back to a normalization on how to heal. They realize legacy circuits aren't going away, and how do we deal with them? So more speed. The other interesting technologies are wavelength division multiplexing, where, we have a single piece of fiber optic cable, and we could send lots of different light frequencies, which means you get terabits of data across a single fiber, where, again, we were talking about one baud, and now we're at terabits of data.
Amazing.
Yep.
Paul, what do you think?
Yeah, I think we're going to see wireless play more into the utility.
Like 5G?
Like 5G, exactly.
Really? You're going to trust your power system to AT&T?
So private 5G, I think.
All right. Private LTE.
Yeah,
all
private
right.
LTE,
Now you got me excited.
I mean, that's exactly the challenge.
AT&T is my cell phone provider. Too. They do a good job. It's just I don't want them running the power system. That's my only comment.
And I think I would echo those concerns. So, the 5G promise, just to kind of, maybe for those that are less familiar with the terminology, but 5G, fifth generation cellular, is promising very, very low latencies. And what they do cleverly is, rather than have the data path take the long way back to some central point, so you think of the cell site maybe being local to where your house is, and what it's going to do is take a long path, it could be hundreds of miles away, back to a switching center, to then be passed back over the network back to its destination. So it allows you to keep that data very local to the cell site. Advantage being you get this very low latency. Combine that with a private system, so you've got your own frequency, your own essential private network, and it then reduces the cost of communication. You don't have to trunk in a fiber optic cable to get that data to your substation site. So I think we're going to see some advantages and some benefits of wireless. And then back, just jumping on what Ken was alluding to or talking about, this wave division multiplexing. I think for me it's a cost performance advantage that's going to happen. I think we're going to see the cost of some of these technologies get low enough that they'll be more widely applied. And I think, that's an exciting one as well. I think this idea of having an optical light path, for certain applications.
Well, you guys are the ones creating all this opportunity with really fast and convenient communication channels. I look at, say we take private LTE, like you mentioned before, from a utility standpoint, they get to own the whole infrastructure. It's a big cost to overlay a private LTE system over a service territory, but you start looking at, now they can control their own cell phone. So if there's an emergency or something like that, they don't have to worry about, everybody trying to call their mother when they're trying to work during a hurricane or something like that, or some other natural disaster. So they have the guaranteed bandwidth they need for their communications. We talked about running protection systems over it. I think there's some other opportunities there too. We build faulted circuit indicators. Wouldn't it be great to be able to hop onto the private LTE network because it has a broad coverage? We could really start looking in depth at how the power system is performing and drive it to some optimal state throughout the entire operating territory. I think there's some huge benefits to that. If we just look at what are some other needs for bandwidth, it's really nice to have video inside substations, or if we have a private LTE system, we can put video out on farther out on the lines if we want to look for fires or other things that would help the public out. So having these accessible, secure, reliable, deterministic, and dependable communication networks only goes to benefit us as consumers of electricity and our local folks like Avista that give us such good service could make even better service. That's kind of my prediction 5-10 years from now. There's a lot of wealth of opportunity out there. We have the ubiquitous communication channel that different assets can jump onto.
We can connect a lot more sensors and smart devices and collect a lot more information and paint a much finer, detailed picture of what's going on in the power system. I think that's excellent. And I hope that your cell phones both work tomorrow.
Well, when this goes live, let's see if it is. AT&T is a great provider for my cell phone. All right, gentlemen, thank you very much for the fun conversation this afternoon. And I'll get you back in 5 years or 10 years to see where your predictions come out, and we'll see what the communications in critical infrastructure looks like then. Thank you.
All right, thank you.
Thanks, Dave.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.